Hi everyone, thank you for coming to our seminar. Today, please join me welcoming Dr. Mekides. Dr. Mekides is a visiting assistant professor at the Color Science Laboratory at RIT. She has received her PhD in signal and image processing from the University of Poitiers and Technicolor in France. And her research bridges high dynamic range imaging, machine learning, color science, and material appearance modeling with a focus on preserving realistic visual appearance under challenging imaging conditions. So please join me welcoming Dr. Mekides, and the stage is all yours.
Thank you. So I can try to be here so that you can see me more. So as Dima mentioned, my name is Mekides Assefa Adebe. So today I will be presenting for you, especially my work related to high dynamic range imaging, more specifically on the reverse tone mapping issue and overexposure correction. But just to give more detail on my background, so I did my bachelor science actually in Ethiopia in computer science. And then after that, I was able to get a scholarship in Erasmus Mundus scholarship in European countries. And then it was the European Union program. So I get to study in Norway, Spain, and France, and also Finland, actually, even though I didn't.
Would you be able to make them closer to you?
Okay.
Just because your voice doesn't go down.
I think I should hold it like this, otherwise it doesn't work. Yeah. So, yeah, so my master's was in color informatics and media technology, mainly color science, computer vision, and imaging, color imaging application related courses and projects. And then after that, I did my PhD in France as a safer program of French government to the collaboration between industry and universities, French universities. So my PhD was mainly related with, University of Poitiers and Technicolor R&D office in France. And then after that, I was able to get a job back in Norway and TNU, where I did my master's as well, my master thesis. And then I worked there as a researcher for around 4 or 5 years after my PhD. And now, maybe 3 years ago, I got the position as a Richard S. Hunter assistant professor of color science, appearance, and technology in the Munsell Color Science Laboratory here in RIT. So in these positions, I have been doing since my master's thesis, I have been doing several researches related to color imaging, high dynamic range imaging, also perceptual appearance modeling and measurement, the video conferencing related works, especially on enhancing the quality and content-aware retargeting kind of applications as well. And I was also working on some color science, applied color science for medical diagnosis. One example I could give is detection of jaundice for really newborn babies based on their skin color. We were able to detect their jaundice label using smartphone cameras. Yeah, so this is, I'm still continuing my research in high dynamic range imaging and material appearance here in Munsell Color Science Laboratory. So today I will be presenting my work in high dynamic range imaging, in particular in reverse tone mapping. So before, I would like to give a background on reverse tone mapping in general. As most of you know, that the light level of our environment is very high, which is really challenging even for our human visual system to look through it in a steady state.
That's not going to be on there.
I can see it here, so.
Yeah.
Okay. Do you want me to say okay?
It's not, I can't click on it.
It's okay? Okay. So in without any, I mean, at a steady state, we cannot see through all these light labels, but through adaptation system we have in our visual system and in our visual cortex of our brain, we are able to see actually all this wide range of dynamic range, but and also a lot of physiological responses we have. But if it's a camera, it's another story. For the camera to be able to capture that big, high dynamic range real world scene is challenging. Of course, the camera industry is progressing. We have a lot of high-end cameras these days, which in one shot can capture a higher dynamic range, but still in one shot, it is still hard to really capture when you have really challenging high dynamic range scene. For example, outdoor scene are still challenging for even for high-end cameras. So what cameras do is like we do using different dark and light adaptations. The cameras also can change the settings, exposure settings, shutter speed or aperture. You can control the amount of light coming into the camera. And by changing the sensitivity of the sensor as well, you can capture different amount of details depending on the lighting conditions you have. And also what we do in high dynamic range imaging is that we actually capture multi-exposures by changing different light levels in the scene using our camera exposure settings. And we kind of do exposure fusion, fuse them together, a weighted average of them to create a well-exposed image of it. Like we can capture details actually both in the dark region and the very bright region of the image by merging all those exposure brackets that we took by changing the settings. And also, like if we have a scene measurement or a proper radiance, scene radiance calibration with our camera, we can also have a scene referred radiance data from the image we just fused using overexposure correction. So basically, indirectly, we can acquire high dynamic range image and even with radiance measurement sense than just intensity or 8-bit data. We can actually have the corresponding radiance values by having a proper calibration. But then the issue is not only the capture, but then we need to, when we talk about imaging pipeline in general, we need to store the captured information or radiance values. And then maybe later on, we might need to show them or print them out. So the different imaging file formats have their own limitations, but probably not that might not affect a lot on the dynamic range aspect of it, only on the quantization and bit depth aspect of it might be challenging on the format. But other than that, it's the displays which are more challenging to really reproduce all the radiances we captured through multi-exposure fusion. So usually for main standard application like streaming or broadcasting, or even manufacturing standards, they will be assuming a display referred image or video formats. And then if you see those standards, the intention is not actually to recover or to reproduce the radiances we captured in an absolute radiometric sense. So that because it's impossible to do that because the display technologies are not capable enough to reproduce all that brightness level we have in the real scene. So we need to basically reduce the dynamic range for these display standards. So because of that, the intention is not accurate radiometric or accurate colorimetric reproduction. It's more of accurate appearance or perceptual accuracy that what they are looking for. So that's the intention behind. And there are so many issues when we talk about rendering, like it's not only the dynamic range, there is a gamut issue as well, the color gamut of the display. But in this talk, I will be only talking about the dynamic range, basically the luminance range capability of these displays. So talking only about the dynamic range for HDR imaging, so we have two concerns, like we have two routes that we need to do at this moment because right now we have both HDR and SDR standards at home. Everybody has TVs, computers, our phones also use different display standards. So some of us might have HDR screens, some of us might have still SDR screens. So I also expect this will also take longer until we kick out the SDR technologies completely, because the HDR technology is not catching up fast. So I would expect this way of operation will remain for longer time from now on as well. So that means if there's a device interoperability which need to happen. So we have cameras which will capture HDR scene, and we have cameras still capture in SDR mode. And because of all the standards as well, even if we have HDR cameras, we are still saving the image or the videos in display referred mode. So the display referred formats are still SDR standards. So that means they are going through tone mapping operations, which will basically compress the dynamic range of the real HDR scene into the display, into that SDR standard format, so that they can be displayed or they can reproduce the appearance of the scene properly. And we also have another route, which is when you have LDR content, which are captured by older cameras. For example, if it's personal use, there are still people commercial use. There are still people using DSLR cameras or smartphone cameras, which are still in SDR standards. But if we are moving into movie production or broadcasting, they probably are using high-end HDR devices right now. But if you go to the YouTube or on the internet, there are actually the majority of the content is actually SDR. So you don't see a lot of HDR content right now, unless like a streaming company purposely created HDR content for HDR purposes. So that means that this route is still important. That means we have to adapt the LDR content we have to the HDR display. For example, if I want to watch YouTube videos or on my HDR screen at home, then I can look at it as it is. But if I change it to HDR format, then the operating system or the YouTube software color management module has to do something so that that video will be enhanced and use the full capability of the HDR screen I have at home. So that's what we call that is a exposure, dynamic range expansion operators or inverse tone mapping operators. So we call them in the industry. So just to give a quick definitions, I'm sure most of you know this. Just tone mapping means if you have a real radiance, you can actually linearly normalize it to your display level, right? So if my display peak luminance is only 200 nits, and my real scene or my image, the scene referred value for my image, the peak luminance might be 10,000 nits. So how can I display that in my 200 nits? So you can just linearly compress the peak to be 200 nits by normalization, min-max normalization, and then it will look like this. So basically, because by nature, usually emissives or specular highlights compared to the diffuse white are very, compared to the diffuse white, their luminance range is really high. Like the ratio between these two is very high. So because of that, usually it's the brighter highlights which will end up being visible in your SDR display unless you do tone mapping to it. So when you apply tone mapping, that means you are compressing a lot on these specular highlights so that you can see the diffuse part of your scene properly on your display. So that's what the one result of the tone mapping looks like after Reinhardt's sigmoidal tone mapping. So there are lots of tone mapping operators because for a long time now, we have been only doing tone mapping because we have good cameras or we have good HDR capturing techniques that we can capture HDR scenes, but there haven't been a lot of HDR displays. So because of that, there was a lot of tone mapping been proposed in the industry and also in the standards to create this scene referred data into display referred. There's a tone mapping incorporated in the color management module itself. So because of that, most contents right now we have are tone mapped or captured with SDR. So the tone mapping by itself actually leads to color clipping and also remove details in the highlight regions or in the areas where we have more brightness than the diffuse white would have in your scene. But in HDR, what I want to also maybe I will mention it later or I skip it without mentioning. The most important part is this self-luminous or emissive components of the scene. That's what makes a scene HDR. So if you have only diffuse content, I don't think we can call that HDR. So to make the scene HDR, you need to have bright areas or bright objects which are more reflective or more emissive than diffuse white. So this is a perceptually differentiating aspect of the HDR scene. So, but by tone mapping, we are removing most of that. So you can imagine if you have an image like that and already tone mapped or an image captured with SDR cameras, basically remove details in those areas and also compress the brightness a lot in those areas, and there's a lot of color issues in that areas, then you want to reproduce that image back to HDR. That's what reverse tone mapping is doing. So if we are talking only about the luminance range, so for example, you can do one-to-one, as I told you before, like in any lightness space. Because it's SDR, we will assume that it will have maybe 100 or based on the standard, if it is a movie standard, it could be 40 nits peak luminance. Or if it is streaming standards or broadcasting standards, it could be 100 nits. For example, sRGB is 100 nits. So you can map that 100 nits to your HDR display, because your HDR display could have up to 1000 nits peak luminance. So you can just map 100 to 100 and you can still see the SDR image as it is. But you have more space after 100 up to 1000. You can use that space to really enhance and boost the appearance of your SDR scene to be able to like because the HDR is the display is capable, so why not use the full capacity of the display? So that's why we the usefulness of reverse tone mapping. So the most common one is just to do the min-max stretching of the luminance to the display peak. So if it was 1,000 nits, 1,000 nits would be stretched to 10,000. Then, I mean, 1,000, the 100 nits of the image would be stretched to 1,000 nits of your display if the peak luminance is 1,000. So just linearly expanding like that, or you could do a piecewise operator like that, because as I already mentioned, that the highlight is very important, and usually the difference between the highlights and the diffuse is very big, even in the HDR scene when you measure the luminance. So the people who have this idea to have a piecewise operation, like for up to diffuse white, we can just use linear scaling. But then after that, for headroom or for bright highlight areas, we can boost it more so that it can correlate with the real world appearance of specular highlights. But I mean, every operator has its own issues. But ITU recently proposed that this recommendation that they have properly evaluated different reverse tone mapping operators for luminance expansion, and they propose this one, which is basically a linear expansion, if you could see it. So we have also performed I don't know what happened on this area, but it was not supposed to be great. But I just wanted to show the highlight region highlighted areas to show how the reverse tone mapping I'm sorry, I mean, it was really important for you to see. I don't know what happened, but in my slide, this didn't happen. But yeah, so the sky was really blue, very saturated blue when you have tone mapped image. Usually tone mapping leads to high color saturation. But when you do the reverse, like when you expand the luminance, then the color becomes desaturated. So that's one issue in color science. We know that effect. It's usually there are different perceptual effects related to luminance and chroma, luminance and saturation. So because of that, when you increase luminance, the color becomes desaturated. So you need additional saturation improvement to get back to the real color appearance reproduction. But there are different variants to do. So you can choose different color spaces. For example, here I said lightness, but lightness could be in different color spaces. So we have different perceptual color spaces in color science. So these color spaces are proposed for, appearance accuracy, reproduction accuracy. So it really depends which color space you use for this in order to reproduce accurate appearance. So because of that, actually, there are people recommended different variants of reverse tone mapping by choosing different color spaces, different color appearance models to work on the luminance in, basically. But we did evaluation comparing all these ITMOs, reverse tone mappings, and we were able to see that most of the simplest ITMO, which is just a min-max normalization, is this one, was outperforming most of them in terms of observer preference. So people were choosing HDR images created through this simple min-max optimization. But one thing I wanted to notice is that none of them are really preferred, even not close enough to the HDR ground truth image. So people always like the HDR, even though we expand the luminance range of the LDR as high as the HDR reference or ground truth. That is because of we have investigated, and that's because this LDR image has already gone through color clipping and detail loss because of tone mapping or because of camera limitations. when we expand the luminance label to display it on HDR screen, we don't really recover any details, or we are not getting back any clipped colors. So we are only expanding and boosting these artifacts even more. So compared to the ground truths, people really don't like it that we don't have details on those overexposed regions. So the quality, the image quality, and the preference is really ranked low compared to the HDR scene, because HDR has full complete detail compared to the clipped ones. And also the color desaturation is also disturbing, as people mentioned to us. So this content loss of content is not only for people preferences. If you consider applications like computer vision applications, where we have, for example, autonomous driving, for example, the cars will be driving through different illumination conditions. Sometimes they might be challenging. For example, even in our taste, we used to have this video where the car will go through a tunnel, and then outside you have a very bright, and while you are in the tunnel, the dynamic range will be very challenging in that particular scenario, for example. So there will be a lot of overexposure outside the tunnel. So that means if there is no detail, the camera is not seeing anything. So it's really hard to bring back details in that type of situation. So for different imaging applications, as well as computer vision, in addition to reverse tone mapping applications, so bringing back details or overexposure correction is very important. So now I will go through my overexposure work that we have been doing so far since my PhD, actually. During my PhD in Technicolor, we were investigating how can we adapt legacy content to the new HDR display screens. And then this was one of our part, because the loss of color and loss of detail was very important to recover for that particular work. And we identified that in natural image, there is a correlation between RGB channels, like in the same spatial location. If you look at the profile of each RGB sensor intensities, they are actually correlated, spatially correlated. So whenever there is a color clipping happen, usually it's not all the channels clipping. It might be only the red sensor, the red part of the sensor is clipping, or it might be the blue, it might be the green. So in most cases, if you have, let's say, only one channel clipped, you can see the rest of the channels, and they act in the same way. So we have noticed that, and also other researchers actually showed statistical correlation between these three channels in natural scene images. So we wanted to basically take advantage of that and propose a color clipping correction and overexposure correction. So what we did is that, and also they should be semantically related regions for that correlation to be valid. If they are not semantically the same, like if it is not the same object, the same spatial location, the correlation doesn't work. It could be different structure between these RGB channels. So what we did is that we identify semantically correct areas, and for each region, I'm sorry, again, this is happening again. I think wherever there is animation or something, there is this pinking appearing. I don't know, it's not in my slide, maybe it's because of the system here, but I don't know, can you see inside the I'm trying to show that what we are doing in here is that for regions where we have only one channel clipping or two channel clipping, so we will be going into the other channel where we still have useful information. So we are copying that and put it to the other channels because we know that they are correlated. So if we repeat the same variation in those clip channels, it should work, like it should give us the detail back. And but when we have three all channels clip, like sorry, here, for example, when you have this type of highlights or highlights clipping or overexposure like this, then we have no channel with information. So everything is clipped. So what we did is for those areas, we just like the bitwise operation, we just boost the brightness of those areas. We didn't even try to recover anything. We just expanded the luminance level of those areas because the expectation is they were white, more than diffuse white. That's why they are clipped. So if we increase the brightness level, then it will perceptually have some contribution, even though we don't have any detail. So that's what we did here, and then do some bilateral filtering to have a smoother transition around the border. And then the results were really impressive. What you need to consider here is that we did this for reverse tone mapping. So after we do the correction, we expanded the dynamic range, and we have seen these results on HDR devices, and it's even more impressive on HDR displays. But just to show you on the screen, we have to tone map it. We have to tone map it back, and yeah, the algorithm was really simple and real time, but it was performing almost better than some of more complex algorithms we had at that time for these applications. So, yeah. So, for example, this is just showing this is a Bayesian-based method proposed by someone else. And this one creating a lot of artifacts, and also the flickering problem was clearly visible, but our method was more stable and no artifact and very simple in real time as well. And actually, this algorithm was patented for Technicolor. So still though, the real issue is overexposure, which is basically when you have everything clipped. Then what we need to do then, so for example, in this example image, we have nothing outside the window. So even if we do the 2 channel, 3 channel, we don't have any information to recover in that. So our correction is not giving you the best result in this type of scenarios. So conventional methods, including in painting, were really not successful for these applications, because even for in painting, like I'm talking about in painting, a conventional in painting method, not using deep learning or AI. So those in painting methods were still dependent on the content, similar content to appear in the same image so that they can in painting from that. But when you have no related content in the image, then it's impossible. So that's why actually not only us, other researchers are also looking into deep learning solutions to basically help bring back details on those highly overexposed areas, severely overexposed areas. So one of the earliest work was using convolutional neural network, like a simple structure like this with CNN, and you have a ground truth. And you should note that the ground truth is also the SDR image, but well exposed. That means you have detail in all areas of the image. And then they clip that, or the exposure bracketed so that it will be overexposed for the training purpose. And then they do CNN. So And one thing you need to note is also the loss function. So it's not a normal like many deep learning applications, they use different loss function depending on the application. So in this case, they are trying to capture the structural differences and the contrast, local contrast differences using the SSIM based similarity measurements as a loss function, in addition to pixel by pixel L1 norm differences. So the L1 norm doesn't capture really structural differences, which is important for overexposure correction or bringing back details. So one other interesting thing they did is that in addition to trying to change the loss function and also using convolutional neural networks, they did another way of convolution, which is a dilated convolution, which has higher receptive field than the normal convolution module, because so convolution, how it works, it only considers local variation, but our severe overexposed regions sometimes require global attention. It might be higher in size than just, let's say, 3x3 neighborhood or 5x5 neighborhood of. So convolution cannot capture the global variation in this exposure level or illumination level. So their way of attending to that is by using a dilated convolution, which has a bit higher strides than just a normal convolution operation. But I don't think so. This helps also to give good results like we had in the conventional method, cross-channel correlation method. But for severely overexposed regions, it's still not powerful enough to recover details. And then there were other people trying to recover based on, because they think that if we could do Laplacian pyramid decomposition and then do the training in each layer, maybe we can capture better structural similarities than just, local convolutional neural networks only on the global image. So they tried this using the unit-based autoencoder for each layer. And also another interesting thing they added is that different loss functions for different components. So they added the pyramid loss. It's the same pixel by pixel L1 norm kind of loss, but based on each pyramid, each Laplacian labels, which different frequency contents will be evaluated corresponding to its labeled ground truth image. The other one is the adversarial loss. So at the end of their network, they have additional convolutional layers, which used as a kind of a discriminator, kind of in generative adversarial network, just to calculate the adversarial loss. So they think that by doing this, they can capture the global appearance or lighting change in the ground truth, like the probabilistic distribution of the ground truth. They are trying to make the generated image to have the same distribution as well by having this adversarial loss. So they were really hoping to really capture the appearance better with this loss function than just the normal L1 norm or L2 norm losses. So basically, the results are good, but as I suspected, in terms of detail recovery, when you have only like smaller regions or slight overexposure like this, it could do really pretty good job in recovering back details and colors. But the question of, so this is supposed to be the ground truth, but the reproduced image looks good in terms of general quality, but if we are considering appearance match, still not the same like the ground truth, but which one is the real one? I mean, which one is more like the real scene? That's like another question, because sometimes I will tell you later in the ground truth in their data set itself, I have seen problems. So probably that's why I'm saying like, this is the output of their models. But for me, I feel like this is a good rendering than this one. But according to their ground truth, this is the ground truth. This is the HDR, not HDR actually. Their ground truth is not HDR, but well exposed from raw image, uh, chosen by experts. So this one is chosen by the experts to be really good image. But for me, if you ask me, I would probably prefer this one. So like what is a good output in terms of color appearance is also one interest that I am looking into in my research. But in terms of content reproduction or regeneration, it does good until we have like severe cases like this. So basically, this input image, as you can see here, is overexposed a lot. So for me, if we don't have a powerful model to recover this type of scenarios, for slide clipping, I already showed you that the simplest correlation, RGB channel correlation method, real-time method was performing already great for those situations. So I want the deep learning to be more powerful in recovering this type of image. But it seems like convolutional network in general is very limited when it comes to image generation for this type of scenarios. I have done before also like try to taste this generative adversarial networks. They're also like another variation of convolutional networks. And my results also showed, and also my perceptual evaluation of them showed that not good results, especially, I mean, when we have severely overexposed regions. Another thing is also, you know, the semantics. CNN is not respecting the semantics. Like, for example, it's not understanding that this is supposed to be a face. So this type of limitations you can see in CNNs in general. So color and content fidelity is impossible like to capture as long as you are using convolutional neural networks. That's at least what I observe. And the semantic incoherence is also a very big problem, and it's probably related to, you know, how much the attention, because it needs a global focus done in addition to the local processing. And as I mentioned, the dataset also have a big issue. I will talk about that at the end. Maybe that's because of that it's generalizing poorly when we have that type of severe overexposure conditions. So yeah, so recently, because of the introduction of transformers, there are also researchers coming up with different solutions to use, because as I told you, CNN is limited because of lower attention span. So, but in terms of that, transformers are known to have higher attention spans. So this particular work, for example, what they have done is they combine CNNs and the advantage of CNNs, which is the local details, and also transformers, which is capturing a global relationship between the different semantically related contents. So for the local processing, they use actually just convolutional layers, both based on Dove's convolution and also pixel-wise convolutions to have more local structural representation. But one more thing they did is they have the trainable gain, bias, and matrix transformations of the colors of the image in their model as well. So basically, this is related to what we do in color science, actually, in camera characterization, for example, when we capture color targets and you're trying to estimate a 3x3 matrix to represent the color transformation. And also you will also have a gamma and again, like gain offset gamma model, we call it when we do camera characterization, actually. So it seems like they're trying to do that, but for the global gain offset gamma model, they are using the transformer block, but it's a single block. It's applied over the whole image. So trying to capture the whole lighting condition of the whole image and to have a transformation for that. But then the image will also go through, basically, these results will be used for white balancing and color correction transformation. And then the gamma will be applied for basically exposure adjustment of the image content. Then finally, the local details and combined with the white balance correction and the gamma application will be their output. So these methods are not only intended for overexposure correction, but also for low light image enhancement. So they're doing both. So they're actually intended for enhancing the lighting, the ill exposed images to be well exposed. Basically, it could be low light condition or it could be overexposure. So in their overexposure results, they show some interesting results still, but it seems like even adding one block transformer is not enough to recover severely overexposed image, and they didn't give any result, but we did evaluated their method in our in recent experiment that one of my students did recently. And what he did is that he created from our HDR dataset we have in our lab, created by Professor Mark Fairchild. We created different overexposure levels of the same scenes, and then we have evaluated the Laplacian pyramid-based method, the transformer-based method, and also a unit-based overexposure correction for reverse tone mapping. So we applied this method first to correct the details, and then we expanded the luminance levels of this image into HDR, and then we displayed them on HDR displays, and we asked people to basically rate their preferences. So according to that experiment, we can see that almost all of the approaches, their performance becomes lower when we have higher exposure levels in the image. But whenever we have a very mild exposure, all of them are doing good. But not powerful enough though when we have a very high overexposed image like this. So maybe the solution could be to use more transformer blocks, which is like a vision transformer, for example. There's an image processing transformer, which only, I think, yeah, we can structure that as encoder decoder, and we can have more attention span, could be localized with a combination with CNN, and that would probably help improve the prediction. Another thing is that even transformers, we have seen that they are really limited in terms of generating or hallucinating new content. So I think for when you have severe overexposure, because there is no information in the image, even though you have longer attention span, you need to hallucinate something, right? So based on the whole data set that you are learned on. So I don't think transformers also have enough capability to hallucinate or generate new content into those areas. But we find out that the recent diffusion models are really powerful in terms of bringing up contents and hallucinate. But the problem with those diffusion models is also they can hallucinate anything. And so semantically that they're a bit off. So we need something to control the semantic nature of whatever they are hallucinating. So maybe for that, we can use the transformer and CNN in combination. But for hallucinating and generating content in those areas, we could use diffusion models. But another issue is how can we control that whatever content we are recreating is actually perceptually accurate. So for that, even if we have adversarial loss, I don't think that's enough. So we need more perceptual oriented loss functions. It might not be just, you know, a metric. It could be another model, which will be basically trained perceptually. So there are already some VGG-based network perceptual metrics, but even that one is only trained on for image quality. That means on image, outside different image artifacts. So it's not like overexposure in a sense. It's trained on image which their quality is degraded by applying, let's say, noise or flickering or some sort of color deformation or hue shift or not a lot of severely overexposure represented in those data sets. But in general, like their intention is for image quality evaluation. But relating that, how can we apply them to be really used for high dynamic range rendering, especially for reverse tone mapping as a loss function? Would be really interesting research, and that's what we are looking into. And one thing that I mentioned is the data set. So all of the models we have been evaluating for have used this data set. So it's proposed by MIT, and it's a raw image. So the ground truth is a raw image, but from the raw image, they did basically exposure bracketing of the raw image. And they have created, to pick the ground truth, they have created 5 exposure bracketing, and they ask experts, like I think 5 experts, I don't know what type of expert they are, but to choose the good exposure that they think is well exposed according to like artistic intent or different characteristics. So they chose the image, and that's the image they used as a ground truth for their dataset training. And then as you can see here in this dataset, there is overexposed image, there are well-exposed images, there are also low light underexposed images. So all those overexposure methods were trained on the full image. So this will basically lead into data bias, because if you really want to have exposure correction, then you need to have more representation of those severely overexposed images in your data set. If your model cannot see that more times and trained on it, then the generalizability will be, of course, it will be low. So one of my suspicion is maybe this data set is really low in number of severely overexposed images. So maybe that's why it's not, the models are not performing well. In addition to, you know, the limitation, architectural limitations of those models. So because of that, we are creating, we have been preparing our own data set, but there have been like this HDR photographic survey done by Mark Fairchild, but it's a very small set of images, but we are creating data set from that, and we are also increasing more from other colleagues, for example, in motion picture science recently. We have received some HDR contents, because we believe that we need to have really a representative scene-referred ground truth if we really want to have applicable models for high dynamic range image. So they have to be trained on, the ground truth should be HDR image as well, not well-exposed image. So to really have a meaningful and also physically based kind of rendering, so we need more HDR ground truth image. And also for the ground truth loss function or quality evaluation, we need more perceptually aligned data, basically having a perceptual score of the quality level of perceptual accuracy of this image. So there is a lot of work in color science to really define appearance differences, but most of those work are not differentiable. So the problem is to have something which could be differentiable and could be applied into these models so that we can have, back propagation and work properly. But my task is basically to really find a midway of doing both. So yeah, so this is a work progress right now. So maybe in the near future, when I have good results, we don't have good results yet, I will be happy to come here and present it for you. So in general, in the future, I see like AI applied a lot to really automate end-to-end HDR rendering or in terms of HDR related applications. And also, as I already mentioned, some of the perceptual issues, I see already researchers going into that direction, trying to have more perceptually valid loss functions. So that would also be, I think, improve in the future. And I would like to see also the generative AI in general or generative models in general to be more perceptually aware. For example, if I want to create an HDR, I want to create an HDR image with this type of contrast label and with this type of brightness label and like that, I would able to tell the model and it will understand me and give me that kind of output. Right now, it doesn't do that. And maybe if you think about, for example, if I want to have, let's say, I want to generate a bottle with this amount of transparency or glossiness or specularity in it, and I want the model to understand what I mean perceptually and then create that for me. So, but right now, that's not the case, but I see new researches in that direction, perceptually aware models. And yeah, so in the future, I feel like there will be more improvement in this regard. Yeah, do you have any questions? I would be happy to answer. Thank you for your attention. Yeah.
Is there a strong understanding of like what aspects of scenes are most likely to give rise to these like flipping in all three channels? Because I was trying to think through this, like, the example you gave for like the sky, they get flipped in all three channels, or like vegetation outside the window. But like, are those? I'm kind of wondering, are those like representative examples of like where most of the clipping in images comes from, or is it just like a lot more random? Because I mean, I'm just kind of like, it kind of seems like if most clipping happens because it's like the sky being overexposed, then you could just fill in some random sky texture and people would be fine with it. It kind of like a model of like what's the most likely like parts of seeds, or other semantics, or like something else that lead to overexposure.
That's really a good question. I think as a color scientist, I think that's what I need to do to train the model where to look for this type of situation. But as we know, like from imaging science as well as we know, and also from color management aspect of it, I tried to mention a little bit, but we know that cameras used to focus or they do auto exposure correction, for example, these days in our phone. So you know that what they are looking for when they adjust their exposure labels, right? So they usually look for faces, for example. So that would be the focus. If there is a face, that would be the first focus. And then they want to make sure that there's well exposure in that region. And then that means most of the sensor sensitivity is dedicated for that region. Anything much more brighter than that will end up clipped or removed. And also when you think about color management, when we do tone mapping, so for example, the new PQ and HLG standards for HDR streaming applications, for example, what they do is there's a concept called headroom. So it's like up to reference white, which is diffuse, perfect diffuse white. You get to keep all the details. even though the scene was captured with HDR in the beginning. But when you convert to display referred cases, and then what they say in the standard is that anything above that could use the headroom. But if the headroom is smaller, you get to clip it. So that means usually above diffuse white, what type of scenes are in there? We know that's like specular highlights or it's emissive components or it could be a light source or it could be emissive colors as well. So we know that those will be clipped out. So this would be really good guide, for example, for the model to look into. Yeah. Yeah.
I just thank you very much for the talk. It's really informative and great. My question is about underexposed images. So you showed that that's the pipeline that eventually could generate this. What about underexposed? When you don't have information, whether it's dark and underexposed or simple underexposed, this noise.
Yeah, yeah. Yeah, I think so. The underexposure cases also, there's some similarity. Like, I mean, most of the models I presented, they really do a good job when it comes to enhancing low light conditions, because in the low light condition, you have information in there. It's just that you just need to boost the lightness level to be able to see more details. But the overexposure case is that especially 3-channel clipping, everything is going to, you need to hallucinate in most of the cases. But for underexposure also, the similarity comes when there is detail, when there was supposed to be a detail at the noise level of the camera. So every camera, we know that it has a lower limit as well, which is a signal to noise ratio 1 is a standard. Below that will be clipped because it is noise, so we don't see anything. So I have never seen any work trying to recover that type of detail. So what the low light enhancement, what they are doing is whatever little information you have, you try to boost them. But if it was clipped because of noise, I haven't seen any work yet. Yeah.
So there was a slide earlier and it showed Bayesian-based method and the correlation-based method, and there was lots of flickering in the Bayesian one. Do we have a similar comparison for transformer-based methods? Are they good for video data?
That's a good question because I haven't seen any transformer-based method for video. Like I mean, in that regard, because I haven't seen any, I cannot tell. But always, you know, the flickering. For example, for the Bayesian, of course, the prior is always it might be different based on frame by frame, so you cannot really smooth it out sometimes. But maybe there might be a way to smooth it out, you know. But this particular author's method probably didn't do that, and that's why we are looking at the flickering aspect of it. But that part is really like easy to fix, for if you ask me. So for transformers as well, it should be fixed by applying it for if it is video and deep learning. I wouldn't recommend frame by frame kind of processing. You can really extend it to 3D model, like the convolution can be 3D convolution transformer. I don't know, it could be also extended into number of frames than just one frame, you know. So this way you can actually smooth out to avoid this type of flickering in video. Yeah.
Similar question. Are there any psychometric data sets on video quality?
Yes, there are a lot actually. So for image quality, there are a lot. For video quality, there are a lot. In color science and image quality community, we have a lot of metrics and a lot of algorithms to actually predict image quality, which are accurate enough with people's ratings. The issue is how can we use that with these deep learning models, you know, because most of those quality metrics are not differentiable, so you cannot use them in here. But there's a really increasing work in that community as well to come up with something which could be used for deep learning community as well. Yeah.
Earlier on in the presentation, you had a slide that showed the transform for the tone scale remapping.
Mhm.
And it was an L max and L min
Yeah.
to a gamma.
Yeah.
Was that a straw man one, or the one that you use, or the typical one?
Yes, I think that's the simplest one, but also the most accurate one, like the most people preferred or chosen one.
So you take the XYZ and you create a lightness signal.
Yeah.
Then you make a lightness transform.
Yeah.
What happens to the color data? What happens to the non?
The chromatic information, yeah. Yeah, so that's also like interesting because in tone mapping and reverse tone mapping in HDR in general, people only worry about the tone reproduction, not a lot on, it used to be like that, not a lot on the color, the chromatic aspect of it. But now, because we have a very big gamut, even though like the primary gamuts, like the RGB gamuts are not big enough, just because we have higher luminance range, the whole color volume is now bigger than the sRGB color volume. So as I already showed in some of my results is here, it would have been really great if you see the LDR sky here, then you will see what I mean. So when you expand luminance, as I already I try to mention perceptually as well, when you increase brightness of an object, the color appearance also changes. The chromatic appearance also changes a lot.
I guess what I'm asking you is, you've got this linear XYZ value.
Yeah.
From that, you computed a nonlinear L value.
Yeah.
From that, you computed a new nonlinear L value.
Yes.
And you still have this linear XY
Yes.
value. In this nonlinear L value, you've got this transform of Y for the L, I guess. But
Yeah.
but you have your color information. How does that get transformed into a new XYZ or run it into an RGB? I mean,
Yeah.
it seems you've got this nonlinear,
Yeah.
and then you've got these two linears. How do they get processed to become the new XYs or
Yeah.
YZs or however?
Yeah, that's really, I mean, a good question, because that's why we needed the color space. For example, I was mentioning here that you could do that in different color spaces and then see the effect, what effect it will have on color appearance, not only in dynamic range, but the color appearance. So the color space, we assume in color science, when someone proposes a color space, it's basically there will be channel independence. That means there are these different attributes. We have lightness perception, we have chroma perception, we have saturation, we have hue, right? So this is different. So for example, if I am doing this in LAB color space, so I will have LAB. So we think that if I do anything in L channel, in the lightness channel, nothing happened to AB channel.
Okay,
They will remain the same.
okay.
So perceptually they are orthogonal. That's
Okay.
what we assume. But in reality, they are not. Like, there are still some effect to each other. So that's why you see here, when you boost the luminance, the color gets desaturated. So at the end, when we render it, we need to get back that luminance back to the AB. And then this LAB will be converted to RGB again. That's the RGB we will see. So just because we did something on the luminance, nothing on the AB, then the color looks desaturated.
So LAB, is 0% reflectance to 100% diffuse reflection.
Yes.
But you're mapping this to HDR data
Yes.
in the input. So how do you do an LAB with something that has a reflectance of 10,000?
Yeah, so LAB is still, that's like you're hitting on the very important question right now in HDR in general. As I told you, like for example, PQ and these new standards, they have different diffuse white labels and things like that. But in case of LAB, as you said, it's proposed for diffuse materials. So they assume that for any diffuse, the maximum luminance is from the perfect diffusion material. So that's why they say it's like the whatever reflection from that is a reference white, right? That's why we use 100 nits perfect diffuser reference white. But when you have contents above that, what happened? Of course, the L will be higher than 100. You can still use the same formula, but still will be higher than 100. So that's what we are doing. But how can we match that diffuse white to the display? So as I told you, for PQ standard, for example, in the standard, they say that this 100 diffuse white should be matched to your display 203 nits. That's the label you have on your display. Even though your display have a peak luminance of 10,000, you should still match that reference white to 203 nits. The rest is considered as a headroom for specular highlights. So like anything above that could be just expanded to your peak luminance. It could be 1,000 nits display, it could be 10,000 nits display. You can just boost everything above that. So that's the standard recommendation, but is that good or not? Right now I'm doing an experiment with one of my students by creating HDR scene, which has color contents, emissive contents way above this diffuse white. So we are trying to render this with different reference white, and of course it has an effect. For one thing, our display in this lab is 1,000 nits. So, but our scene is above 1,000 nits, it's around 10,000 nits. So most of these colors are clipped out when you have diffuse white mapped to 203 nits. So what should we do on that headroom, not to clip things? So that's really like, I am also doing research in that regard. Yeah. Any more questions? Yeah.
So like you mentioned like in MIT that they said that there's a balance of the over and underexposed images. So like have you considered synthetically generated your own data set?
Yes, like because capturing HDR content is very difficult, like especially if you want to have representative scenes of the whole world, you need to go out and also indoor, outdoor. We already have like a limited number of HDR scenes captured like that, properly calibrated and properly have a scene referred data. So we base most of our data sets on that. But we are thinking like to increase our computer-generated HDR scenes as well. Maybe we may need to include that to expand the number of data sets. Yeah. Okay, so there's no question. Yeah, thank you very much for inviting me.